Welcome to the second module of this Unit 2, Permutations and Combinations, and we will be defining and discussing about what are permutations in this module. Okay. For that, we'll start with a simple example. Okay. Consider the objects A, B, C, D. Okay. I have four objects here, A, B, C, D. How many different arrangements can be done during this using this four objects? So I have this A, B, C, D, four objects. How many different arrangements, or in how many different ways I can arrange these four letters A, B, C, D? Okay. Now if I have to do it manually, now this A, B, C, D is itself an arrangement, or the way I can place this A, B, C, D here, these four letters. So the same way I can also arrange them as A, B, D, C. Okay, what I did was this C and D, I changed their places, and this, by doing that, I got a different arrangement here. So moment the positions of C and D were changed, I got a different arrangement here. The same way I could have written this as A, C, B, D, or A, C, D, B. Now B appears in the third position. In the earlier first two arrangements, B appeared in the second position. In the next two, B appeared in the third position. I could have also written them as A, D, B, C or A, D, C, B. So depending on where each of this letter is appearing, you will see that I get a different arrangement here. Okay, so Permutations talks about the arrangement of this type, where an order is important, the position where I am placing a particular object is important. Now, all these arrangements are with A as the first letter. Okay, instead of A as the first letter, I could also write this as B, A, C, D. In that case, I will get six different arrangements here: B, A, D, C. Or B, C, A, D. In that case, B, C, D, A. Or B, D, A, C. B, D, C, A. Depending on where I am writing a letter, every different order in which I am placing them gives me a different arrangement. Again, I get six different patterns when with B in the first place. I got six different patterns with A in the first place. The same way, I may have C in the first place. In that case, with C also, I'll get six different arrangements: C, A, B, D, C, A, D, B, C, B, A, D, C, B, D, A. Okay, so like this, the next two. These are with C. Okay, I may write C, D, B, A. C, D, A, B. These are with C is the first place. Then D, D, A, B, C, D, A, C, D, D, B, A, C, D, B, C, A, or D, C, A, B, D, C, B, A. So depending on, so these are all with A in the first place, B in the first place, here C in the first place, and D in the first place. Depending on which position letter appears, accordingly I got a different arrangement, and you will see that these are all the possible arrangements that I can get with these four letters A, B, C, D. In total, these are 6, 6, 6, 6. Total 24 arrangements, or 24 different patterns that I can get from these four letters. Okay, so what permutation tries to do is, it gives us a formula in computing this directly without having to do it manually like this. If I have to do it manually, I have to write down all the 24 possible arrangements as you see. So what permutation says is, if I have n objects, okay, I had four objects there, and taken R at a time. Okay, so the permutation of n objects taken R at a time is the number of ways R objects can be arranged out of n objects. and it is denoted by the notation either P n comma R or NP R. So basically I have total n objects, out of which I am arranging r objects. Okay, so in the previous case we saw that there were 4 objects A, B, C, D, and I was arranging all 4. So there n was 4 and r was also 4. In that case, this permutation or this number of arrangements can be given by this formula. P n r is equal to n factorial upon n minus r factorial, or in this notation you will say npr is equal to n factorial upon n minus r factorial. Okay, so this is so in the previous case I had 4 objects, 4 letters, and I wanted to arrange all 4. So that's how I had to arrange 4 letters out of 4, or we were trying to arrange 4 letters taken 4 at a time. As per this formula, it will be 4p4. So n is here 4 and r is also 4. It will be 4 factorial upon 4 minus 4 factorial, which is 4 factorial upon 4 minus 4 is 0, 0 factorial, which will be equal to 4 factorial is 4 into 3 into 2 into 1. 0 factorial is 1, we know. This is 1, and 4 into 3 into 2 into 1 is 24, and that's how we get this. So while in the previous slide we did it manually and we saw that there were 24 arrangements possible using these 4 letters, permutations will directly give a direct formula in computing this number of arrangements. So permutations talks about arranging, how many different arrangements are possible of n objects taken r at a time. Only thing is that you have to remember that we are assuming that all the n objects that we are talking about are distinct. That is one assumption that we are doing here, and one object is selected only once. Okay, so these are the 2 assumptions based on which we carried out all this arrangement, the options or the patterns. Okay, so in general this is how we define permutations of n objects taken r at a time. Okay, so the number of ways 4 objects A, B, C, D can be arranged. We saw that it is 4p4. There are A, B, C, D, 4 objects. We are arranging all 4, and we already saw that this is equal to 4 factorial, which is equal to 24. So if I have to select only 3 objects, the number of ways 3 objects can be arranged out of A, B, C, D. So instead of arranging all 4, I am taking only 3. So I may take A, B, C as the 3 objects, and with A, B, C itself, this A, B, C will give us 6 different patterns: A, C, B, B, A, C, B, C, A, then we have C, A, B, and C, B, A. So if A, B, C will give me 6 patterns, then I may also take A, B, D. A, B, D again will give me 6 patterns. I may take A, C, D. A, C, D will also give me 6 patterns. So instead of doing it manually, permutation definition says, if I am arranging only 3 objects now out of these 4 objects, it can be done in 4p3 ways. Okay, so by definition it is 4 factorial upon 4 minus 3 factorial, which is 4 factorial upon 4 minus 3 is 1 factorial. 4 factorial is 24, 1 factorial is 1, I'll get 24. And obviously that will be true. With A, B, C I have 6, with A, B, D, with A, C, D I have another 6, and with B, C, D I'll get another 6. So 6 plus 6 plus 6 plus 6, I'll get 24 patterns. With permutation formula, we can know the answer directly. So in case I am arranging only 2 objects, the number of ways 2 objects can be arranged out of the 4 objects A, B, C, D. So there are total 4 objects. We are arranging only 2. It will be 4p2. By definition, it will be 4 factorial upon 4 minus 2 factorial, which is 4 factorial upon 2 factorial. 4 factorial is 4 into 3 into 2 into 1. 2 factorial is 2 into 1. This 2 and 1 will cancel. I'll get 4 into 3, 12. Okay, and these 12 are referring to AB, BA, AC, CA, then we have AD, DA, then we have BC, CB, then we have BD, DB, then we have CD, BC. I am taking only 2 objects here. So these are the different arrangements that are possible when I am taking only 2 out of these 4 objects, and these are the 12 arrangements that we are referring to, which we are directly getting as per this formula. If I have to arrange only one object, then I can take either A, B or C or D. I have only 4 options. By formula it is 4P1, we are arranging only one object out of 4. So it will be 4 factorial upon 4 minus 1 factorial as per the formula. 4 factorial upon 4 minus 1 is 3 factorial. 4 factorial, now I can write down as 4 into 3 factorial divided by 3 factorial, that will cancel, I'll get 4. And obviously these 4 arrangements are either A or B or C or D. We are arranging only one object. So this permutations gives us the number of ways we can arrange n objects taken r at a time with that formula. Okay, so if I have to consider this example, find all possible different arrangements possible using the letters of the word computer. Okay, now these are 1, 2, 3, 4, 5, 6, 7, 8. These are 8 letters. Okay, and all of them are distinct. And we are arranging all the letters. Find the possible all possible different arrangements using all the letters. So it is using the letters, so it is referring to all letters. So these are 8 letters, and we are arranging all 8. So it is like 8P8. It is equal to 8 factorial upon 8 minus 8 factorial, which is equal to 8 factorial upon 0 factorial, which is 8 factorial. Okay, so 8 factorial is 8 into 7 into 6 into 5 into 4 into 3 into 2 into 1. This will be a number 40320. Okay, in fact straight away when you wrote 8P8 here, you could have directly written 8P8 as directly 8 factorial. In general, NPN is straight away n factorial. Okay, so that could be remembered. The same question if I consider in a different way. Find all possible different arrangements possible using the letters of the word computer. It's the same word that I'm considering here. So that C always occupies the first position and R the last position. So we are now trying to arrange these 8 letters 1, 2, 3, 4, 5, 6, 7, 8. Okay, such that C always occupies the first position. So C is always here, and R the last position. So R is here. So C is always here by default. R is always here by default. So I have to only arrange the remaining 6 letters in this remaining 6 positions. So I have to arrange 6 letters. How many ways I can arrange these 6 letters? It is 6P6, which is 6 factorial. 6 factorial will be 6 into 5 into 4 into 3 into 2 into 1. That will come to 7. So it's the same question with some conditions that I put. Accordingly, this is how I have to just arrange those remaining letters in these 6 positions. So it is same as saying arranging those 6 letters. Okay, in any number of ways. So it is 6 factorial, which is 720. Okay, so if I consider this example, find the number of ways 9 books can be arranged in a shelf. So you have a shelf, okay, and you want to arrange these 9 books in this shelf. So basically I have something like 1, 2, 3, 4, 5, 6, 7, 8, 9. I have these 9 positions, and I want to arrange these 9 books in these 9 positions. So it is like arranging these 9 books or 9 objects anyhow. So what will be the answer? It will be 9P9, straight away 9 factorial. 9 factorial will be equal to 9 into 8 into 7 into 6. So that answer can be found out. Okay. Note that we are assuming that all the books to be distinct. This formula of permutations that we are using here, okay, it is with an assumption that all books are distinct. Only then we can say that there are 9 factorial number of ways I can arrange these 9 books in a shelf or in these 9 positions. Okay, so this is how we can use this permutation formula in arranging objects. Okay, and we stress that permutation talks about arranging the objects, or the order is important to us. Okay, note that we did not always jump to the formula. Okay, like how every time we had an example, we directly jumped to the formula of NPR, permutation formula, and we found out the number of ways. Like if I go back to the number of ways 4 objects can be arranged out of A, B, C, D. So basically we wanted to arrange these 4 letters in 4 positions like this. I have 4 positions A, B, C, D. Okay, so I said directly it is arranging 4 objects, so it is 4p4, which is equal to 4 factorial, which is 24. Okay, this permutation is actually a direct form of the principle of counting. Okay, the rule of product. Now if you see the first position here, I can place any of these 4 objects here. Okay, so this first position has 4 options. Okay, now one of these 4 I place here, so this first position has any of the option of these 4 letters, out of which I'll place here 1. So the next position I'll have only 3 letters available. So this can happen in 3 ways, or any of the remaining 3 alphabets can be placed here. So 1 will be placed here, so 1 alphabet is gone here, 1 alphabet is gone here. The next position I have only 2 alphabets that are remaining. And then finally the last alphabet will appear here. So the first place here has 4 options, the second place has 3 options, the third place has 2 options, and the last place has only 1 option. So if this can happen in 4 ways and 3 ways, and this can happen in 2 ways, and this can happen in 1 ways, all this can happen in 4 into 3 into 2 into 1 ways. This is equal to 24, and this is exactly 4p4. So this 4p4 or NPR that we are writing is actually the result of the rule of product, the fundamental principle of counting. So every time we are solving an example on permutation, we did not directly jump to the permutation formula. In fact, we may manually see how it is actually happening. The same way, if I have to say the number of ways 3 objects can be arranged out of A, B, C, D. So now I have 3 positions to fill. Now I have 4 letters. Now in the first position here, I can place any of these 4 letters. Okay, so I have 4 options for the first place. 1 letter will be placed here. So the next place will have only 3 alphabets available for 3 options. And the third place will have only 2 alphabets here. So this can happen in 4 ways, this can happen in 3 ways, and this can happen in 2 ways. Altogether, they can happen in 4 into 3 into 2, that is 24 ways, which was exactly 4p. So this NPR is as a result of fundamental principle of counting. So you may do it always. We may not be always get the direct answer in terms of NPR formula. We may always have to look at how it actually works out using the rule of product. Okay, so this formula, probability of permutation of n objects taken r at a time, which is here that we wrote, is actually the rule of product that we are following. Okay. So if I have to consider this example, how many ways 4 men can go into 3 different hotels so that every hotel has exactly 1 customer? So there are 4 men, A, B, C, D, and there are 3 hotels, 1, 2 and 3. So if I have to find out how many ways these 4 men can go into this check-in in these 4 hotels such that every hotel has exactly 1 customer. So I don't have to really jump to the permutation formula. I see that the first hotel, so any of these 4 men can go in this. So the first hotel has 4 options. Okay. 1 person will go here. Then the next hotel, I'll have only 3 men. available, because one person has already gone here, so this hotel is out of option after that. So those remaining 3 people, whichever other 3 people remaining, they'll have only it will have only this hotel or this hotel to do. Okay, so the second hotel will have any of these 3 options. Any of the 3 men can go here, one of which will go here. In that case, the third hotel will have only 2 men available, only 2 options. So altogether this can happen in 4 into 3 into 2, 24 ways. What we are doing is we are solving not in terms of the permutation formula straight away, we are putting in terms of the principle of counting, okay, the rule of product.